All right, excellent. This last question is about uniform circular motion and friction. So it actually involves two different things. And we haven't done an example quite like this that combines these two very different concepts. So I thought it'd be a nice way to kind of marry these two topics. So here's the question. What's the maximum speed a car can round a 25-meter radius curve, and it's a level curve, so it's not banked in any way, and they give us the coefficient of static friction as 0.8 between the tires and the road. Now, why is it the coefficient of static friction? This is a really subtle point here. When you think about the type of friction that comes into play when you have a tire, right? This is the tire, this is the road. Here's a tire, and here's a road. There's something subtle. It's not quite the same as like when you have a block on a surface. When you have a block moving on a surface, this is obviously kinetic friction because you have relative motion between these two objects, right? You have, if you were to sort of zoom in on the block and the surface, there's relative motion between the two. But with a tire, it's a little bit different. With a tire, the tire itself is actually rotating, and so if you were to zoom in kind of on the interaction between the tire and the road, there's actually no relative motion between the two, or there shouldn't be if the tire's not slipping. So as long as the tire's not slipping, the tire's rotating, there's actually no relative motion between the two, in which case the type of friction that actually matters is static friction, not kinetic friction. It's a weird thing, but something that's important to this question. So here we are, we're dealing with static friction in this particular problem. And excellent. And so what we're doing is, I'm thinking about how does this involve circular motion? Obviously they're talking about some sort of a radius to a curve, so there must be some kind of curve here. So if I were to view this curve from above, and here's my car, it's going to travel in some kind of curve, and there's some radius to that curve. Something like that. Okay, so the same way that I've got, if I were to swing a ball on a string in a circle, right? The string is the thing that actually is keeping the ball inside the circle. So it's the thing that's exerting what we call the centripetal force in that particular case. Here, with the car on the road, the thing that is keeping the car in the circle is actually friction. It's the friction between the car and the road. If there were no friction, right, they've probably driven on icy roads before, then it's much harder to drive it in a circle. Instead, you just end up sliding off in a straight line. So the reason that we're able to keep this car moving in a circle is because there is a friction force, and friction force is the thing keeping us in the circle. So it's actually our centripetal force here. So there it is. Here's our friction force, just like that. All right. Excellent. So we've got some givens here. They told us that the radius is 25 meters. They told us mu s, seems weird, is 0.8. And they didn't really give us any other information. But they did ask us for the maximum speed here, the maximum speed that we would be able to sustain with this amount of friction. So this mu s really relates to the maximum amount of friction. So when we have max friction, that's when we're going to have the maximum velocity, right? The faster this is spinning, the more friction we're going to need in order to keep this thing moving in this circle. Excellent. Okay, so we've got some ideas here. So in this particular case, it seems like the way to analyze this is to think about this in terms of centripetal motion. We said that centripetal forces are any forces that point towards the center of the circle. Now, of course, there are other forces acting on this car, right? If I were to view the car, front-wise, basically, like here's the windshield, and here's like the hood of the car, and the headlights, or whatever, and the little tires or something. There are also forces, so here's this friction force. This is the one that's keeping the car in the circle, but of course there's also a gravitational force downward. I don't know how big to draw that as compared to the friction force. And then of course there's also the force of the road on the car, force of road on the car. So there it is. So we've got these three different forces actually acting on the car, but only one really comes into play when we're dealing with the circle. It's exactly the same as when we have the ball on the string and we whirl it in a horizontal circle. We don't care in that particular case about gravitational forces because they don't come into play unless we're dealing with a vertical circle. So here, the only centripetal forces that I have, the only center-seeking forces that I have are actually due to friction. So here we go. Our centripetal force, again, we think about the centripetal force sort of as a net force. It's like a net force, where our directions really are positive if it's center-seeking, negative if it points away from the center. Center-seeking and negative if away from the center. Now in this particular case, the friction force is pointing towards the center of the circle. Since it's pointing towards the center of the circle, that is our centripetal force. That is the thing that keeps it in the circle. So that's why we have a positive value here. If for some reason we had some force that pointed away from the center of the circle, then we'd write Fc equals negative whatever that force is. And of course we've dealt with situations where you have more than one force that's contributing or taking away from our centripetal force. And that's an example of like the vertical circle. So I'd encourage you to take a look back at that if you're curious about it. So here we are. Okay, so our centripetal force is our frictional force. It's kind of a weird problem because we often don't combine these two things. So here we go. We've got an equation for centripetal force. Centripetal force, again, we're thinking about it like a net force equation. It's m times a, where a is our centripetal acceleration. So this guy is m times our centripetal acceleration, but we know that that is just m times v squared over r. Cool. This is always, always, always true for centripetal forces. 100% of the time we can write Fc equals mv squared over r. Now in terms of the friction force, let's take a look at that side of our equation. The friction force, in fact, we're interested in sort of the max friction force, and for the reasons that we talked about earlier, it's going to be technically a static friction force, even though the car is moving. And again, that's because there's no relative motion between the tire and the road. It's sort of a strange thing when you zoom in. But here it is. We're dealing with the max static frictional force, and this is mu s times whatever our normal force is. So when we're thinking about what our normal force is, I actually want to look at this picture, because the normal force is the support force from the road on the car. So the normal force, in this particular case, is the force of the road on the car. It's not always true that our normal force has the same magnitude as our gravitational force, but in this particular case it is. And so here, this is mu s times mg. And again, the reason that we know that they are equal here is because those are the only two vertical forces, right? The only forces acting towards the center of the Earth and away from the center of the Earth, basically. And so they must balance each other out. We don't have any vertical acceleration, right? The car isn't accelerating upward or downward. So these two vertical forces must balance each other out. All right, okay, so now we have kind of a lot going on here. Let's bring this all together. So I'm going to bring it all together. So we said our centripetal force equals our friction force. So this is our centripetal force. And this over here is our max static friction force, mu s mg. Fortunately, there's a mass in both of these, which cancels. That's great because they never gave us a mass, so happy to see that. And so this must be then our maximum velocity. And the reason, again, it's a maximum velocity is because we're dealing with the maximum static friction force. So if it's okay with you, I'm just going to write max here in the subscript. And now I'm just going to solve for v max. This is the thing that I'm looking for. So I'm going to bring the r to the other side, mu sg times r. And then I'm going to take a square root of both sides. So technically I get a positive and a negative. But since I'm dealing with a speed here, that's really the thing I'm looking for is the magnitude of this velocity. I know it's got to be positive. Magnitudes are always positive. So V max is going to be square root mu s gr, which in my case is, I get 14 meters per second. All right, I hope that helps.